Imagine a beaker of water sitting in a vacuum chamber. As the pressure continues to fall, something astonishing happens. The water begins to boil and freeze at the exact same time. This phenomena is known as the triple point of water. In this video, we will explore how scientists discovered this bizarre behavior, the physics that makes it possible, and why this point is so fundamentally important, not just for water, but for how we define temperature, pressure, and even reality itself. The triple point is a term in thermodynamics that refers to the precise condition at which a substance exists in all three states of matter, solid, liquid, and gas, simultaneously. For water, this occurs at exactly 0.01 degrees Celsius and a pressure of about 0.006 atmospheres. At this unique combination of temperature and pressure, the water molecules are in perfect equilibrium. Ice, liquid water, water vapor coexist, simultaneously changing from one phase to another. It's like watching nature juggle with atoms, freezing here, boiling there, all at once. And this isn't some rare quirk. It's a fundamental property of matter. To understand how scientists discovered this, we need to go back to the 19th century, a time of great advances in the field of thermodynamics. It was the French physicist Pierre Curie, working in the late 1800s, who played a key role in understanding phase transitions. But it was through the development of the phase diagram, pioneered by scientists like Thomas Andrews and James Thomson, that the triple point was truly conceptualized. In 1873, Josiah Willard Gibbs, one of the founding fathers of physical chemistry, published a groundbreaking paper titled Graphical Methods in the Thermodynamics of Fluids. In it, he mathematically modeled how substance changes phases and introduced the concept of equilibrium lines and points in a pressure-temperature diagram. From this work, it became clear that there must exist a special intersection where solid, liquid, and gas lines all meet, a triple point. This wasn't just theory. By the early 20th century, scientists were able to recreate this in the lab, thanks to advances in temperature control and vacuum technologies. The triple point of water was so significant that it became one of the reference points in the definition of the Kelvin temperature scale. Let's get a little deeper into the science. Every substance has a phase diagram, a map that shows how it transitions between solid, liquid, and gas depending on pressure and temperature. For water, the triple point lies at the intersection of three curves: the melting curve, the sublimation curve, and the vaporization curve. At the triple point, these curves converge. The system is in equilibrium because the chemical potential, the energy per molecule of each phase, is identical. That means there is no net change between any two of the phases. Molecules are constantly freezing, melting, evaporating, and condensing, all at the exact same time. But how can water boil and freeze at the same time? Here's how. Under extremely low pressure, below 0.006 atmosphere, the boiling point of water drops significantly. If you reduce the pressure while maintaining the temperature at around 0.01 degrees centigrade, liquid water will begin to boil, turning into vapor. But at the same time, the low pressure means the heat energy required to keep water in liquid form is also gone. So, it starts freezing. In some experiments, you can literally watch water bubble and form ice crystals at once. It's one of the most beautiful visualizations of thermodynamic balance. In fact, for decades, the triple point of water was the gold standard used to define 273.16 Kelvin. The triple point isn't just some scientific curiosity. It reveals some of the most counterintuitive truths about our universe. At the macroscopic level, we are used to thinking that freezing and boiling are opposites. But thermodynamics shows us that under the right conditions, opposites can coexist. It's a reminder that the laws of the universe aren't confined to our intuition. They are governed by deep mathematical symmetry and balance. Moreover, the triple point teaches us that phase transitions are not just about temperature, but pressure, energy, and molecular dynamics. Water in particular is astonishing. Its phase diagram is unlike any other common substance. Ice floats, water expands when frozen, and it has not just one triple point but 17 different crystalline phases of ice, each with its own exotic triple points. Understanding water's triple point helps scientists model conditions on other planets, calibrate instruments on Mars rovers, and even simulate the conditions inside neutron stars and high-pressure materials. And perhaps most importantly, it forces us to rethink about the boundaries between different states of matter. Even something as stable as water is full of surprises.